In this lecture, we're going to discuss numerical solutions and in particular Euler's method for approximating solutions to differential equations. First of all, let's talk a bit of a bigger picture. Analytic solutions to a differential equation is what we have been discussing so far. They are explicit formulas for the solution. So we have actually considered two cases, y prime equals ky and y prime equals a minus by, the two cases where we were able to find the exact formulas for the actual solutions. In the first case, it was y naught e to power kt, and in the second case, it was a slightly more complicated formula, but still involving an exponential function. These are the only two equation types that we're going to know the explicit solution for. In other cases, we have not derived the formula for the solution, and sometimes we're not even able to do that because the differential equation itself is so complicated. In those cases, because we cannot find the explicit formula, we're going to be looking for numerical solutions, and rather approximations. So we're not going to get the exact right answer, but we're going to approximate it and hopefully approximate it well enough. The one method we're going to consider in this course for the approximation is Euler's method. And this is very similar to the linear approximation method you guys have seen in Calculus 1. The main idea behind both Euler's method and linear approximation method is the fact that you can approximate the curve or the function itself by its tangent lines. So if we're thinking in terms of the linear approximation from Calculus 1 concept, we had a function, we picked the point where we could construct a tangent line, and we knew that near that point of tangency, the line is really close to the curve. So the points on the line are really close to the points on the curve, and therefore we can approximate one with the other. Now, if we are given a differential equation, it will be, for example, of the form y prime equals something. That means that while I don't know what y itself is, I know the value of the derivative at any point because I can simply evaluate it. The derivative itself, let's recall, is the slope of the tangent line, which means that at any point that I wish, I can calculate the slope of the tangent line. Let's think about what that means on the graph and how we can proceed with that. So let's say my time axis is here and I have some time steps, 1, 2, 3. Normally, with a differential equation, I am also given an initial condition. Let's say that in this case, we're given the initial condition at 0. So I know the value of the actual solution, the y value at the point 0. Now, generally, I have no idea what the actual solution looks like, but let's say for the sake of illustration here, I will know that this is what I'm trying to imitate. Again, we don't actually know the shape of it generally, but here I would like to illustrate it to see how close we're going to get. What the differential equation gives us is the slope of a tangent line at any point. So I'm going to start by building a tangent at this point. I'm going to ask my differential equation for the slope. I'm going to get a number back, and I am able to build a tangent line. There we go. This is my tangent line. Now, from the linear approximation back in Calculus 1, we know that if we stay close enough to the point of tangency, then the tangent line is going to be really close to the actual graph, which means, for example, if I calculate at 1, this is the exact solution, and this is the approximation. They're fairly close to each other. If I now go further away at 2, I can see that my solution is now further away from the approximation. This gap is going to be getting bigger and bigger and bigger the further away I move from the point where I've originally constructed my tangent. So what I can do, though, is repeat the exact same construction at the next point of my choice. So let's say I go to 1. I take the actual point of approximation at 1, and I'm actually going to give it a name. Let's call it y1. The first one is the exact value of the initial condition at y naught. The next one is along the tangent line. So this is my approximation. This is the exact solution, but I'm not too far off. What we're going to do at y1 is reiterate the same process. At y1, we're going to ask our differential equation for the slope of the tangent line. Now it's going to actually give us the slope of the tangent line to the original curve. So the tangent is here. Remember that same slopes will produce parallel lines. So here, building from this point, I'm going to get the line that is parallel to the solution curve. So I can build my second tangent line here, again parallel to this one. And I can now travel along this line to calculate the approximation value at 2. So now looking here at 2, the exact solution would have been at this point, but my approximation is now at this point. This is what I'm going to label as y2. Notice that building a new tangent line produces a much better approximation than following the original tangent line. If I followed the original at 2, my approximation would have been here, which is really quite far from the exact solution, and my new approximation of y2 is really much closer to that. And I can again repeat this process as many times as I want. So I can build another tangent line at y2 by asking my differential equation for the slope. It will give me the slope that matches the solution curve, so mimics its shape. So at this point here, the slope will be something like this, which means the tangent line built from y2 is going to be parallel to that. And I can then, at this point, at 3, calculate the value for y3. So again, note that at all of these points, these are my exact solutions. And the y1, y2, and y3 are the approximations. What becomes clear in this process is that using a new tangent line every time allows for better approximation, because using the new tangent line ensures that the new point is close enough to the point of tangency, as opposed to using the first point where the tangent line sort of loses track of the shape of the actual solution. Keeping with the new tangent line every time ensures that my sort of zigzaggy line here really mimics the shape of my curve all the way around. This is kind of like building a straight line figure to mimic the very smooth function that is the solution. It also becomes clear that the smaller your step size here, the better your approximation is going to be. So what I have here are step sizes of, let's say, 1. If I insist on making even smaller steps, then my tangent lines are going to mimic my curve even closer, which means that my approximation points are going to be even closer to the exact points on the curve. So these two are basically the main two considerations behind the Euler's method: recalculating your tangent line at every step and taking smaller steps if you want better and better approximations. Let's now take a look at a particular example so we can see how this works with the very specific graph and the very specific function. So here we're given a differential equation y prime is equal to 4 minus 2t with the initial condition of 10. We would like to approximate the solution and then compare it to the exact one. So sometimes the function that is given is actually quite easy to calculate the exact solution for. And in this case, we can do that. This way, we can compare how well our approximation method fares against the exact solution. Notice that this is not an equation of the form y prime equals a minus by, because we don't have y, instead we have t, which actually makes this even simpler, because this is something we can think of in terms of antiderivatives. So what is the antiderivative of 4? The antiderivative of 4 is 4t. What is the antiderivative of minus 2t? Minus t squared. And then we will get the constant plus c that we can use the initial condition y naught to calculate. And in this case, because it's at 0, it's going to actually be simply t. So this is the exact solution, and we are interested in approximation of it. So let's see how we can approximate and how good our approximation is going to be. So what we're going to do is follow the exact same steps as we've just outlined with our method, except for in this case, not only do we have a graphical intuition, we also have a formula that we can calculate the exact slopes of. So as our graph suggests, we're going to start with y naught at 10. So let's say somewhere up here, and we're going to take a few steps, let's say 1 and 2 here. So what we're going to do is, first of all, at t equals 0, calculate the slope of the actual tangent line. Y prime at t equals 0, plug in t equals 0 into our differential equation. This will go away, and y prime is going to be equal to 4. Okay, so remember that for this step, you use differential equation. Differential equation is kind of like an oracle that tells you what the slope is without telling you what the curve looks like. So we have t equals 0, we have the slope, and we also know that at that point at y naught, the value of the solution itself is 10, which means we can use all of this information to, in fact, find the tangent line. We can find the tangent line. Now, this is going to be following the exact same calculations you would have seen in Calculus 1. I can take the point-slope form of the line, and I can simply plug in the values that we've just discovered. So what do I have here? I have y minus y naught. Y naught is 10. I then have the slope. The slope, as given by the differential equation, is 4t minus t naught, which is 0. What I get after some simplification is 4t plus 10. So it's a line with a y-intercept of 10, which is good because that's what I have, and a slope of 4, a positive slope, so my tangent line will look something like this. Again, let's say I don't know what the exact solution looks like, and my oracle of a differential equation only tells me the slope. This is not to build the equation of the tangent line. What I'm going to do next is actually compute the value at 1. So right here. This is what's going to become known as my y1. So what we're going to do is plug in t equals 1 into the equation of the tangent line to see what it gives us. So what is that going to produce? If I plug in t equals 1, I get 4 times 1 is 4 plus 10. So this will give me 14. This is my approximation. What if I plug in t equals 1 into my exact solution? What is that going to give me? Let's see. 4 minus 1 plus 10 is going to give me 13. This is my exact solution. Not bad. My approximation produced 14. My exact solution is 13. But what's good about this approximation method is that I can reproduce these steps again at y1 and get the next tangent line and the next one and so on as many times as I'd like. Now again, because in this case we also even have the exact solution, I can draw the approximate shape. I can see that this is a parabola, it's looking down. At t equals 0, it's going to be 10. So my very first point is actually exact and approximation agree. So my solution will look something like this. Okay, an upside down looking parabola, so the tangent lines actually make sense here. Let's try to generalize this method and see how that will work out. What we always follow are these steps over and over again. We start with a differential equation with some initial value. It doesn't have to be at 0, but it usually is. We ourselves get to choose the step size that we will call delta t. It's preferably small, the smaller the better, because smaller step size will produce a better approximation. In the previous example, we chose the step size of 1, but it can really be anything. If I chose the step size, for example, of 0.5 here, then we would simply be plugging in 0.5 into our tangent line, or the exact solution if we have it, but the method doesn't really change. Then we use the tangent line from the current point to approximate the next point. We move to the next point and we repeat all of the same steps over and over again. Now, instead of computing the tangent line every single time, one would hope that we can use this general setup to come up with an equation that we can simply plug things into. So let's see if we can develop that and how that would work. If I start at y0 and I move to the next step following the tangent line, then my next point is what we called y1. Now notice here that I am following the tangent line, which means I'm following its slope for the length of delta t. The slope here is calculated as rise over run, and that is also known as the derivative at that point, y prime. So what I can do is in fact rewrite how I can compute y1 using y0 and the rise over run value for y prime. I notice that what I have is, if I want to calculate y1, I have it's equal to y0 plus the rise that I have actually risen. Notice that I'm only interested in the y value, so it's a little bit easier. Okay, so I have that y1 is equal to y0 plus the rise that has happened in between. Okay, take a second to really appreciate how simple this formula is. Y0, again, because it's just the y coordinate, is actually, you can think of that as being here. So to calculate y1, I simply took the old value for y and added the rise to it. Now, though, what I can do is rewrite this rise in terms of my y prime and this formula right here. I'm going to do it in two steps so it's clear where I'm getting things from. Instead of writing rise, I'm going to write that it's rise over run times the run. So I haven't really changed anything. It's like this run value can cancel out and I will get my y0 plus the rise. But when we rewrite it this way, it's actually convenient because this part of my equation now is what is known as y prime. And this part of my equation, that is the run, is how much I ran from y0 to y1, which is something that we denote as the step size, delta t. So this is my delta t, which means that overall I have the formula y0 plus y prime times delta t. Now recall again that I can repeat this process starting from y1 again and again and again, but nothing about what I've done here is specific to y0 or y1, which means that this formula should hold in general for any value of the y that I'm computing. So this is kind of now reminiscent of Newton's method, where we have that the n plus first value of y is equal to the nth value. So the next value is equal to the previous value plus the slope times the step size. Now, the one thing you gotta keep in mind though is that your slope needs to also be a value, and it's going to be a value as computed at your current step. You're using all the information from the current step to be able to calculate the next possible y value. Let's see how we can use this formula in its all generality to compute with a specific function. So here, in our first example, with the general formula, I have that y prime, or dy by dt, is equal to t squared plus 1. I have that the initial condition is 3 at 0, and I would like to approximate the value of y at t equals 1 with a step size of 0.5. So first, let's just think about that for a second. I am given the value at 0. I would like to approximate the value at 1, so between 0 and 1, and my step size is 0.5, which means I will have to take 2 steps of Euler's method to get from 0 to 1 with this as a step size. Because it's going to be more than one step, I'm going to create a table to keep track of things. So in my table, I'm going to put the value of t, the current value that I am at. I am also going to keep track of my calculations for the y value. So at the next step, yn plus 1 is equal to yn plus the slope at the previous step times delta t. This is the function, this is the formula that we derived on the previous slide. And then I am going to keep track of what is the slope at this current point. So y prime is going to be t squared plus 1 as dictated to me by my differential equation. Okay, so what am I given, first of all? I am starting at t equals 0, and I am given that the y value there is 3. So when t is 0, y naught is equal to 3. This is the given information. That is all the given information that I have. Everything else I'll have to compute for myself. So here I can calculate the slope, and that's the slope that's going to be used not in this step, but in the next step. I'm going to use this information to calculate the slope. So what do I have here? I have t squared plus 1. My t value is 0. So my y prime at this point is 0 squared plus 1, or simply 1. Now, the next value for t is going to be calculated using my step size. So I'm going to be adding the step size here. My step size is 0.5, so my next t value is going to be 0.5. Now, what I'm going to be computing here is y1, my first approximation. I'm going to be using all the information from the previous row to plug into this formula to produce the next value for y. Okay, so I'm going to be using this formula, but all the information from the row above the one that I'm currently filling out. So this is saying it's yn, which is the previous one, so 3, plus the slope at the previous step, which is 1, plus times the step size, which is always fixed at 0.5 as given in the actual approximation. Okay, so note where everything is coming from. Everything comes from the previous line. And again, delta t is actually fixed. So if I calculate this number, what am I going to get? I get 3.5. Okay, now I can extend my line to calculate the actual slope at this point, because that's the slope that's going to be used in the next line. And I know that I'm not done yet because I'm not yet at t equals 1, which is where I want to be. So to calculate the slope here, I am going to once again plug everything into my differential equation, but I'm plugging the best available information. So the just calculated information into my differential equation. My differential equation only uses t value, so I'm going to be plugging 0.5 into here to calculate the slope. So it's going to be 0.5 squared plus 1, and that comes out to be 1.25. Okay, now let's calculate the next step. To calculate the t value, I am again going to be adding the step size, so that will bring me down to 1. I have y naught, y1, so the next one is going to be y2. Now notice that the subscript actually just lists the step number, not the actual t value, which is why I'd like to keep the t column also, because these don't have to be the same numbers here. Okay, and once again, I'm going to use all the information from the previous line, my best available information, to plug into this formula to calculate y2. So what am I going to have? I have that I need to take the previous y value, which is 3.5. So this guy travels down here, plus the previous slope value, which is 1.25, times the step size as per formula, and the step size is always fixed at 0.5. So all of this together will give me 4.125. And again, notice that I'm bringing all the information from the previous line into the computations of the next y value. Now, I was asked to approximate y of 1, so y value at t equals 1, and this is what my y value is. So I don't actually need to go on calculating the slope here. I already have the value that I was asked to compute. So I can make my conclusion at t equals 1, approximate y value. Approximation gives that y of 1 is approximately 4.125. Now the problem also asks to sketch the approximation, and the sketch would normally help us at least get some idea of whether this is an approximation that is an underestimate or an overestimate. Now this will not always be actually accurate, but it is an educated, let's say, guess. So let's sketch what we have computed. I have the t-values go 0, 0.5, and 1. So 0, 0.5, and 1. And the corresponding y-values at 0, I was up at 3. So let's say 1, 2, 3. This was y0. At 0.5, the y-value was 3.5. So let's say up here, this was my y1. And at t equals 1, my y-value was 4.125. So somewhere up here, this was y2. So my tangent lines went like this and then a bit steeper like that. Now recall that the initial value is actually the exact value, which means that the solution curve will coincide with my tangent lines here. And then based on the shape of the tangent lines that always have to be parallel to the actual graph, I can guess that my graph looks something like this. Which means, let me draw my, again, guess of the graph. So this is my approximate solution. This is my best sketch at the solution that I basically know very little about. And in that case, because the tangent lines somewhat suggest the shape that is concave up, this will mean that this, what I have produced as an approximation, is likely an underestimate. Because for a concave up shape, the tangent lines will always lie below the graph itself. Likely underestimate. Now again, this will not always be an exact guess, an exact right answer, but it is the best available guess. Let's see how we can mimic again this procedure with a different example. So in this case, I have that the differential equation is involving both y and t. The initial condition is 0.5. I would like to approximate y of 2 with the step size of 1. So I am starting at 0. I would like to get at 2, but I would like to do so with a step size of 1, which means, as same as the one before, I have to take 2 steps. So I'm going to record everything in the table that is exactly the same construction as the previous time, just to keep track of all the necessary information, all in an organized, orderly fashion. So here, note that my differential equation, of course, changes because I am given a new one, but the way that we compute with things is going to remain the same. So what am I given? I am given that for t0, I have that the y0 value is 0.5, and I can compute the derivative value with this information. So the derivative is y minus t, which means that my y value minus my t value, 0.5 minus 0, is going to be equal to 0.5. Excellent. Now my next t value, because the step size is 1, I'm going to add the step size. That is going to give me a 1. And now, again, I'm going to use all the information from the previous row to plug into the Euler's method equation to produce the value for the next y, which is going to be labeled y1. So what am I going to have here? y1 is equal to yn, so the previous y, which is 0.5, plus the previous slope value, which is 0.5, times the step size, which is 1. So this 0.5 from here, this 0.5 from here, and I have my new value for y1, which turns out to be just 1. I'm now going to compute the next slope, so I can use it in the next line over. So in this case, again, the slope is y minus t, so it's the y value minus the t value. So my slope here is going to be y value, which is 1, minus the t value, which is also 1. So the slope is going to be 0. That's a little bit different, but it shouldn't affect how we proceed with the method. So the next thing I'm going to do is, again, add the step size. This is going to land me at 2, which is exactly where I would like to end, y of 2. and I am going to calculate the y value here. So again, using all the previous lines information, plugging it into the formula. So the previous value for y, which is 1, plus the previous value for the slope, which is 0, times the step size, which is 1. Okay, so what do I have here? 1 plus 0 is simply 1. So my y2 is 1. So the approximation gives me that y of 2 is equal to 1. This is where this is coming from. Now note again that I don't have to compute the slope here because I am not proceeding to the next line, so this is unnecessary. And let's sketch what we get in this case. So I went from t equals 0 to t equals 2 with a step size of 1. And what did we have? At t equals 0, the y value was 0.5. So let's say I have, let's make it a little higher. Let's say I have 0.5 here. This is where I started. At y1, at t equals 1, I had y equals 1. So at t equals 1, I have y equals 1 here. This is my y0. This is my y1. And then at t equals 2, I also had that y2 was equal to 1. And that is because, of course, the slope was 0, which means the tangent line was horizontal. So for y2, I stayed there. And this entire thing was connected by tangent lines to the original solution curve. So this also suggests that if I start here, my solution curve probably looks like this. It looks like this is tracing a concave down curve. And if it's tracing a concave down curve, the tangent lines lie on top, which means that this is likely an overestimate. Now, Newton's method was a very similar iterative procedure to Euler's method, and Newton's method was really easily replicable on a computer, which means that in this case, we can also ask for software to do a bunch of calculations for us. You can simply Google Euler's method calculator and get a whole bunch of websites, and I'm just going to show you one of them. Now, this is the website that I like for Euler method calculation, but you really can pick any one that Google suggests. For whatever calculator you choose, you will have to get used to its notations. So here, it allows me to pick what my variables are called, and I'm going to draw the last example that we just did. So I had dy by dt, and this was equal to y minus t. Now, this website actually has quite a few approximation methods. We in Math 118 will only work with Euler's method, so this is the one that I'm going to pick. This website calls step size h, so I'm going to put that in. The step size is equal to 1, and the initial condition at t equals 0 was y equals to 0.5. I'm going to click submit and see the actual approximation of the solution that these initial conditions and this differential equation will produce. Notice that this is exactly like the curve that we drew the two steps off. Starting at 0, I have an increased slope and then a flat slope. What the software allows us to do is reduce the step size and also do more steps than we would ever care to do by hand. So let's say here, I'm going to now take the step size of 0.5 and focus on the red curve. Notice how it's going to change. See, my step size, and so every jagged little piece got a little bit shorter, and it's also gotten less jagged. With smaller step sizes, my solution is going to, my approximation is going to be much closer to the solution and much smoother as a result. If I reduce the step size more to a quarter, it's going to get even smoother still. So here, let's say I pick a very, very small solution, step size, and I'm going to end up with a very, very smooth looking approximation. Now you can play around with anything here and fix even the window that you actually want to take a look at. So for example, if your t values are only positive, you might want to pick the window to start at that value. And then here, let me emulate our original solution, which was this, an increased slope and then a flat slope. Notice that the curves behind here, the dashed gray lines, somehow suggest the shape of the curve. These are called slope fields, and this is something that we're going to discuss in the next chapter. Now, on the last slide here, you will find additional problems that span the entirety of this chapter 4. There are problems on the solutions of differential equations, there are problems on a couple of applications, as well as the problems for Euler's method. Also, check out this website for yet another way to use Euler's method calculator.